Good morning, all of you. So here I would like to present some of the uh, important tips or some of the idea about a circuit design and PCB design. So let us start with the outline of my presentations. First, I'll present motivation of this presentation, why I'm going to present it. Probably you can also get some interest out of that. Then we'll talk about in brief about the flow of system design process. So whenever we want to make a system, whenever we want to start a hardware design or any product, then what is generally a flow to be followed. Then we'll talk about types of devices in brief. Then we'll come to PCB, or we also call it sometimes layout design. So here we will first talk about noise and EMI EMC issues, the issues what we face while if a PCB is wrongly designed, and then some tips for PCB design specifically for power electronics. So I'll a bit of this presentation will be a bit of inclined towards power electronic design, and why that also will tell you. Then PCB design tools, and in short some glimpse of PCB manufacturing and assembly process. So what is the printed circuit board? So some of the let us start with the history of this. So first, this PCB board started early in 20th century. Then in 1903, a German inventor, Albert Hansen, described flat foil conductors laminated to an insulating board in multiple layers. And Thomas Edison, we know him. All of us have heard about him. He experimented it in 1904. Then in World War II, PCBs are used in aircrafts to withstand the circuits in mechanical stress. Then in 1980s, small surface mount parts have been used increasingly instead of through-hole components. So since if we are talking about PCB, we'll bit of talk about uh, devices. So their surface mount is kind of devices. We'll talk about it a bit in detail in the following slides. So what is the importance of PCB? Uh, See, this presentation, I know many of my colleagues might be already aware of the PCB and they must have done several projects. But I request you, if I am starting from a very basic, then we'll go to a bit really useful stuff. So kindly bear with me if you find it sometime very basic. I kept in mind that everyone and all of us should get a bit of benefit out of this presentation. So PCB provides a home to the components, right? High component density we can get out of a PCB. So this is a picture you can see on the screen how dense it is. This is possible only when we use PCBs. There are other methods, like if we have like 10 components, we can connect them in a breadboard, or we can connect them through any other method, or we can some in some circuit, a very small circuit, we can in fact keep some of them floating. But it is always good to use a PCB as and when we can. So it has, like when we use PCB, higher component density can be achieved, like components per unit area. And if we use multi-layer PCBs, then there will be many more connection per unit volume. Here you can see in the picture so many components, but all of them are connected from either on the same layer, some of them are connected from another layer. It provides mechanical strength to the components, right? Because it is not always that each and every component is very strong. Sometimes if you see uh, if you see, this is a capacitor. Sometimes what happens, the terminals are broken if they are not properly mounted on a PCB. Similarly, there are other components in the PCB which further gets mechanical strength. It helps in high power density design. I'll uh, I'll tell you what is this high power density design. It means uh, a converter or a system is able to process power in how much unit volume. For example, if we have a 10 kilowatt system, so it is processing 10 kilowatt. It is not consuming, it is processing 10 kilowatt. Suppose we have an inverter. Input is battery, output is something else, some AC loads. So this inverter is processing 10 kilowatt power. And what is the size of inverter? So that is considered as power density. The unit of power density is usually watt per cubic inch, or sometime we also consider it kilowatt per liter. It helps in reducing circuit parasitics. So what are these circuit parasitic? We'll talk about this. Why the circuit or PCB design is important to learn. So couple of things like engineering degree without practice, just like mechanical degree without treating patient is useless. It is it is as important as learning a basic C language for an IT or CS engineer. So this is one of the basic things an engineer, I would say an electrical electronics engineer should know. And our country needs such expertise. Most of the electrical electronic system, even if they are very small, they don't really need any expertise to be developed, but they are being imported from other countries, including basic lamp, you can see mobile chargers, the thermometer, all these things are coming from outside India, despite of the fact that we have, I mean, India is one of the largest electrical electronics engineer producing countries. And also we know our population, we are one of the largest consumers also. And why we should learn it? Because undoubtedly it is very interesting, and I would say it is simple. It is not any rocket science. We should do that. So, classification of circuits. So we can say if we have a circuit, so we can broadly classify that circuit in some of the parts. One we can call controller circuit. So they can be separate also, but they can be part of a single system as well. For example, suppose we have a inverter. So that big inverter or any DC to DC converter that will have a controller circuit, which will have either microcontroller or any other controller, its supporting components. Then that system can also have a sensing circuit, which will sense all the parameters required to be sensed or to control. It will also have a driver circuit. Driver circuit, I mean the driver circuit which is going to drive the power devices. So they are different than controller and power. It will have a driver circuit, power circuit, the main power circuit, usually what we see on the paper, like inverter 4 switches or buck converter 2 switches, in inductor, capacitor. So that the main part of the system, main part of power electronic system can be called as power circuit. And if we need communication, then there will be a communication circuit, and if we also need display and monitoring circuits, there will be a display and monitoring circuit. That depends on the requirement. Uh, okay, let us start with the flow of a system design process. First of all, whenever we want to design a product, whenever we want to design a system, what all the process? First of all, we need to identify the problem or the application or the purpose why we want to produce any product. Then we need to develop a block diagram. Being an engineer, we need to develop a block diagram of the system. This is how a system can work. So it will have DC to AC stage, it will have filter stage or whatever. Then key component selection. Of course, there will be hundreds of components, but some of them are very important, like MOSFET selection, inductor selection, capacitor selection, because Other supporting components may come in line with respect to the ICs and other things, but key component selection comes into picture. What is the voltage rating we need? What is the current rating we need with respect to that? Then design of circuit comes. So here, after key component selection, we can start our schematic design. Then layout design comes. Layout, I mean the PCB design, as well as if there is anything within the circuit we need to lay out, we need to have a layout for wire connection, or maybe there are multiple PCBs within a system. So how we will connect uh, each of them with each other like this. So it includes all of them, including PCB design. Then once the design is ready, on the computer, on the system, then the design goes for manufacturing. Then when it comes back from manufacturing, the bare PCB, then other components are mounted on them, the population is done. That process is generally called assembly of the PCB. Then testing is start. If testing fails, then we have to start from point number 2 or probably point number 3 again, this process. If testing is successful, then we can go ahead for production. Okay, so this was about an idea how a system is designed, the process of that. Now we'll talk about little bit about type of devices. So majorly, I would like to classify them in two parts. One is through hole. As you can see here in the picture, all of these devices are called through hole. They have a big lead. Here you can see that lead goes inside the PCB, and from other side or maybe from the same side we solder them. So they will have a drill arrangement on the PCB so that we can fit them on the PCB. They are called through hole devices, through hole components. Other is called surface mount devices. So they don't have any kind of such leads which uh, don't need any kind of drilling. They are mounted on the surface itself. So these devices, surface, such type of devices are called surface mount devices. Here you can see the difference in short. Through hole, which has two drills required on the PCB. These leads are going inside the drill and then they are soldered. While the surface, this is also a resistor. These two, if you can see E01 and EEE, they are also resistors. They are mounted on the surface itself. Their connections are made from the top side or bottom side itself. So there are several benefits of surface mount devices. There are a couple of benefits of through hole devices also. So let us talk about surface mount devices a bit. Surface mounting was originally called planar mounting. Okay. Initially, IBM has worked on it, and first SMDs demonstrated by IBM in 1960. Before that, it was all of them were through hole. Later, widely used in late 1980s. So after 80s, it is started. The use of SMD started widely. At that time, it was fascinating to mount the components both side of a PCB. If we have through hole, then we will have a drill. Then we will have leads of the component which is placed on the top layer. So we cannot place anything on the bottom layer also. But in surface mount technology, we can place devices on both the layers, top layer and bottom layer. So that was really like useful. It becomes very useful. As of 2012, the smaller component size which was available in SMD, it was zero point 0.4 by zero point 0.2 mm. Here you can see some of the SMD components on his hand, and the smallest component I can't even find it with where it is. Maybe this one. Higher density of connections because holes do not block routing space on inner or backside layers. So see, this is suppose we have multiple layers, multi-layer PCB. So if a component is mounted here, if we are not having any through hole drill, then opposite side also we can place a component, and routing can be done within the layers. So that through hole component may block the routing path, but in case of SMD, routing can be done within the layers, right? Okay. So some of the devices we will now quickly talk about, a couple of 5 6 category of the devices. First is in SMD we take resistors. So these are the package size of the resistor, various package size. So if we talk about, let's say, 0603, or we talk about 1206, so they are uh, yes, here we can see if something is written on the register. So this is how we can calculate the value. Like for through hole registers, if you remember, we have those color codings to get the values. Here, these are the methods how we can get the values of the registers, and each package is rated for some volt. So if package size is becoming bigger and bigger, you can see the voltage rating is bigger. So this is nothing but the X and Y uh, uh, size, like what is the size in X, 0, 2, and like 0, 1, or 0, 4, 0, 2 means X side and Y side. So this is a circuit diagram of a high voltage sensing circuit. So no need to go in detail, just one message I would like to tell you. Suppose we are measuring 1000 volt here. We want to measure 1000 volt here. So op-amp is not capable. It is just rated for 3.3 or 5 volt, or maybe sometime 10 volt, 12 volt. It cannot measure 1000 volt. So we connect several resistors in series. And suppose if it is 1000 volts, each resistor should have a voltage rating more than 250. So 250 will be dropped here. So if their values are same, right? That is also important. So this is just to in a crude word, I can say, to step down the voltage. So all will have 250, 250 volt around them. So that much rating we should have of the device. We should select the package size which has the appropriate voltage rating. Similarly, capacitors are available in same package and size as in resistors. There is a trade-off between capacitance value and voltage rating for a particular package. Some types of capacitors like this, these are the ceramic types, these are electrolytic capacitors. So this part, the middle part, shows the SMD component, SMD ceramic capacitors. Here these are SMD electrolytic capacitors. Here they are tantalum, SMD tantalum capacitors. Some of the devices or ICs, like this is their different package name. So this is not IC name, this is just the package name, TQFP. This type of package is called TQFP type package. These type of packages are called DIP packages. They are through hole in a way. These are called SOIC packages. So SOIC 8 means one IC which is like this, which will have 8 pins. These are called QFN packages. These are like CSP, WLP. This is QFP package, and this is WSON package. Just to give an idea, these ICs are having different packages. In single package, there may be different kind of ICs. One could be controller. In the same package, other we can find like op-amp and something else. But package size or packages are standardized. These are some of the power devices. You can see SMD diodes. Am I audible, guys? Just wanted to confirm.
Yes,
Hello?
yes, sir.
Oh, yeah. Okay, thanks. Fine. So these are the SMD diodes. Here we can see these are the SMD MOSFETs. and these are assembly regulators. So you can see some of the packages are same. This and this, they are almost same. Some other devices like inductor and transformers, you can see a small inductor, very small inductor is also available, and some transformers are available. They are mostly all of them are SMD, so there is not much difference in that. If these leads are longer, they will go inside the PCB and soldered on the other side. If they are just flat, they can be soldered on one surface like this. Then crystals are also available in SMD packages. Okay, some advantages of SMD, like quickly I'll go through that. Lower initial cost and time of setting up for production. That is lower. Fewer holes need to be drilled. Components can be placed on both sides of the circuit board. Better mechanical performance under shake and vibration conditions. Many SMT parts cost less than equivalent through-hole parts because size becomes small, so the manufacturing raw material sometimes that is used less. Some disadvantages are also there of SMD. Manual prototype or assembly or component level repair is difficult, requires skilled operators and more expensive tools. SMDs cannot be used directly with plug-in breadboards, right? If somebody wants to just check out on the breadboard how this circuit works, that is like kind of very difficult in SMD. Then SMT is relatively less suitable for high power or high voltage parts. So if voltage level is like really high, suppose we are talking about a converter which is having megawatt rating or hundreds of kilowatt rating. Those devices pertaining to that power level, we might not find any SMT. So they will be through hole or either there will be kind of modules we have to place directly on other surfaces, not PCB itself, just like some other arrangement we need to do for them.